Very exciting. Okay. We're now starting section 5.2. The most exciting section since contradiction. So this is section 5.2, and it's what's called weak induction. Before you ask, yes, there is a strong induction. Yeah. So weak induction, not to be fun of the induction, but it is weak. And that goes, well, before we can talk about how this goes, we need to talk about how regular proofs go to show why it's different. So let's consider a regular proof that proves the following claim. The claim being that for all n in the natural numbers, n is even implies n squared even. Now, you guys had a proof similar to this on your homework. It's actually the opposite. On your homework recently, you said to prove that if n squared's even, then n's even. This is the easier direction. If n's even, n squared's even. And the way you prove that, we've done it before, let's just go through quickly. It goes like this. You say, let n be an arbitrary / particular natural number, right? And then you assume the hypothesis. Assume n is even. Then by definition, is how I'm gonna write this? Actually, let's write it like this. I'm gonna write it in a form. It's gonna all the same words, but it's gonna look different. It's not how you should actually write things in your homework. This is just for us to think about it right now. So we're starting off with n is even, right? And then here's how direct proofs work. Right? We're just going to prove this by direct proof. The way direct proofs work is you start by assuming something has some property. So we have n, and we're just assuming it has the property of being even. And then we're trying to show that property will logically lead to the property that n squared is even. So here's what we're going to do. Because n is even, right, we know that there exists a k and z such that n equals 2k. So n being even, n having the property that's even, by definition means it always has the property there exists a k and z so that n equals 2k. And this is by definition. Now, if there exists a k and z so that n equals 2k, we're trying to show n squared is even, that means that n squared just equals what? 2k squared, which equals 4k squared, which equals 2 times 2k squared. And this is true by substitution in algebra. In actual proof, you put more than this, but we're trying to get the form here. And then what does that imply? Well, since n squared equals 2 times 2k squared, and the actual proof you have to show that 2k squared as an integer or whatever, so skip that part for now. Because it's 2 times an integer, by definition, it's even. So n squared is even. By definition. Therefore, assuming n is even, n squared must also be even for all n natural numbers. So this is the general form. Hopefully this proof makes sense. And the big thing we're doing, right, is just by assuming n has this property of being even, then immediately we know there must exist a k, and immediately we know that n squared is going to be 2 times 2k squared, and then immediately we know n squared is even. These just logically follow. These just logically fall out from n being even. So this is how a direct proof works. All direct proofs go like this for universal statements. They all start by assuming n is some arbitrary element with a certain property. In this case, the property n's even, and trying to show that that property will lead to a property, which will lead to a property, which will lead to the property you want. In this case, n squared being. So here's what I'm going to do. I'm now going to label these with predicates. So let's say this is the predicate Pn. So remember, predicate is a statement. Well, a predicate's a sentence that becomes a statement when you plug in a variable. So the Pn is n is even, is what it's saying. So P of 3 is saying 3 is even, which is false. P of 4 is saying 4 is even, which is true. Let's call this Pn. Let's call this Rn. Let's call this S of n. And let's call this Q of n. And so we can rewrite this as for all n in the natural numbers, n even, same thing as P of n, implies Q of n. So an equivalent way we could have written this proof, put this aside for a second, is we could have just said that let n be an arbitrary but particular natural number, assume n is even. So then we have P of n is true. So really you're assume P of n. Then P of n implies R of n, which implies S of n, which implies Q of n. Therefore, assuming P of n, we must have Q of n for all n and n. Here's the point. A direct proof is a chain of properties, right? Starting from what you know to what you want to prove. And it just works by picking out an arbitrary element in your set with that property and then following the chain that has what it wants. This is a direct proof. So far, I haven't really done anything new. We've just kind of written it weird. Any questions?